We're here for the latest episode of Wrench Tales. We're number 4 already, and I'm with my good buddy Michael Guenther from Downtown Auto Service in Crofton, Nebraska. I get that right?
You got it right.
Awesome. Mike, thanks for joining me today. How you doing, my friend?
I'm good. How about yourself?
I'm good, thanks. Looks like you sounds like you had a little bit of computer trouble earlier today, huh?
Yeah, my computer crashed last week and I just got it picked back up now. So at least they saved stuff so I don't have to redo a bunch of QuickBooks.
That's a plus. You made it out alive. Well, with that, I thank you for taking the time to join me. I know how busy you are. I really appreciate it. Mike is a shop owner and extremely successful technician and diagnostician. And if you don't mind Mike me bragging about you, I would like to share something real quick. Let me know if you can see my screen.
I can see it.
Excellent. Mike has graced the pages of Motor Age magazine recently here in our, I believe this was our February issue, 2024 of Motor Age magazine. He was in my column, The Data Doesn't Lie, featuring a 2007 Ford Edge. And Mike has some really cool diagnostic abilities and shared some really cool testing techniques to speed up his diagnostic process. So, Mike, I thought the article was brilliant, and I really appreciate you, my friend. Thanks for taking the time. It's a pleasure to have you on.
Oh, thank you. I just try to contribute.
Oh, we do appreciate it truly. Listen, so I want to talk about this car you had recently in the shop. You and I spoke about. Can you see this on the screen? Is that showing up okay?
Yes,
You remember this nightmare?
I do. I do.
Mike, this Mike had a 20 no, not a 2019. It was a 2009 Chevy Impala. And I call it the lockdown, making a joke about coronavirus. I probably shouldn't do that. But '09 Chevy Impala with a very strange door lock concern. Um Mike called me about halfway through his diagnosis because he got to a stopping point because his next step it wasn't logical. And I don't mean like he didn't know what he was doing. I mean the next step he wanted to take, the next step that made sense kind of didn't make sense at all because it inferred that all four, not one, not two, not three, but all four power door lock actuators were bad. So after hearing this story, Mike called me. We talked about it. Mike, I'd appreciate if you can walk us through this. I'll cycle through this PowerPoint presentation if you will, but walk us through what's going on here.
So the client had contacted me probably 2, 3 weeks prior to it coming in and was asking about checking her door locks when she would bring it in for service. And so when she dropped it off, she's like, well, you got to check them door locks when you service it because I got locked in my vehicle the other day. And I'm just, it's kind of the classic like Family Guy, where he's, you know, the keys are outside the car and he's locked in, or I think it was Family Guy. It was some cartoon. But anyways, I'm just like, really? And she's like, well, until I pop the
Okay,
lock, you
good.
know.
She she there was a redemption right there.
Yeah. And so yeah, we did the service, our inspection and all that stuff. And then dug into the lock issue. She also added another um it's got a hard fill, hard fuel fill condition as well. So we looked into that. But the locking issue is what really, just not that it baffled us. It just, like you said, it didn't make sense, all four of them bad at the same time.
Yeah, you know something, and I recall you sending me a couple of videos from your what appeared to be your cell phone, what was happening. And what I really appreciate about the videos is obviously I got a visual of what was happening on your lab scope, and we'll talk about that in a minute. But what struck me most is what I was hearing with my ears. Can you describe that? What were you noticing about these symptoms as you were going through your diagnosis?
So after, if you would actuate either lock or unlock, it would just slowly dissipate to where they wouldn't function at all. The click would get quieter, quieter until there was no click.
Now,
And it didn't matter
that
whether you were doing lock or unlock. It was the same way both ways. And then you'd have to let it just sit for a little bit. I
Okay.
mean, it didn't
Now,
take, 30 seconds, and then you
I want
could
to
actuate them again.
I want to ask you a question based on logic because I'm hoping the people viewing this at the shop or at home or are thinking, hearing what you're saying, hearing this description of the symptoms being exhibited, and considering what might be at fault. What comes to mind when you hear about? I'm asking you this, Mike. What comes to mind when you hear a door lock work like this, and then the next time it's like, and then the next time it's getting softer and softer? What are you thinking? And then you say you let it rest and it gets better again after a short period of time. What's
So
going through your head?
my my thought was it was more of a system problem, not an actuator problem. Either
Exactly.
system. I hadn't totally dug into the wiring diagrams yet. System or relay,
Mm-hmm.
something like that.
Something common, right? And
Hmm.
if you all didn't catch that at home, Mike did say all four, left front, left rear, right rear, all four door actuators had the same initial performance, and all four of them degraded slowly over time to the point they didn't do anything. And you let it sit, and then they all come back. So yeah, logic will tell you that there's a failure that's common to all four of those power door locks. So at this point, I mean, we dug into this diagram. Now, I've researched this vehicle previously to put this little presentation we have together so we can talk our way through it. But the first thing I want to point out is the inputs. Um, this is our computer controlled device, and excuse me, these are computer controlled devices. Our body control module in this case is the computer that is going to be processing the input. So look at how this works. These switches are wired to a path to ground, and there's one on the driver's door. um I'm sorry, this is the door lock for the driver. This is the door lock switch for the driver's side, and this is the one for the passenger side. But all of these are pull down circuits. There's a reference voltage supplied here and here and here and here and also here, and these switches will pull those signals low. And we can tell that just by looking at the diagram, but we don't seem to have an input issue. They're clicking just fine. It's just their performance degrades over time. So we're beyond an input problem. I think our problem's on the output. And this is the diagram we're faced with. So, I mean, at this point, Mike, when you called me to tell me what was going on, this is what I was facing here. And looking at this diagram, I'm trying to put together a strategic plan, a game plan where we can limit the amount of testing we're doing. But also, I don't want to test everything. I just want to test where the problem is likely to be. So, considering this layout, I mean, we gotta we got to look how this is laid out to consider some test points. I mean, we've got three relays. One is the door unlock relay, and these are internal to a fuse box. We can't touch them. Um, Printed circuit board relays. We've got a door unlock relay over here, and then we've got a door lock relay. And regardless of which direction current flows, we've got three actuators, uh, right front, left rear, right rear, that all share a common path to voltage and a common path to ground on either side of the actuator, where the driver's actuator is standalone. Ultimately, they all share the same ground path, but initially, early on, these three are together where this one's separate. So, I mean, that alone, we've got to consider some test locations. But you didn't do that right away. You didn't jump directly into voltage testing, and I applaud you for that. We went to current testing. And of course, you included a voltage test for the test point you were at. But what I was really interested in was the current test because, Mike, you know this as well as I do with your experience that current equals the work being performed. So if
Yes,
we're seeing good current, right, the work's being performed. Do you agree with that?
correct. I do agree.
So this is the video that Mike sent me. Now, everybody, I want you to watch the video. And at the same time, I want you to listen. What we are going to have in green is a voltage from a test point, a voltage reading, and in yellow was a trace from the current probe. So the more current that flows through the circuit, the more work that's being performed. The less current flow that flows through the circuit, the less work that's being performed. So take a look at this video. Oh, you know what? Hold on. I gotta share the sound. Bear with me 1 second. Share sound. Mike, you let me know if you hear this. I'm gonna play that video one more time. And again, I want you to watch in green. I made a mistake. There's no voltage being tested in green at this point in time. We are just looking at current. But listen with your ears. When current is high, notice the noise the actuators make. And then when current starts to get lower and lower, listen to the noise of the actuators. We're going to do it again. So considering our observations, Mike, I mean, I've got my thoughts on what's happening here. What are you thinking? Like, what was going through your mind when you saw that current start to degrade like that?
A voltage drop I've struggled with before, so the way I was looking at it, looking at current is as it was going down, it obviously, yeah, it was not doing its job, but I was kind of thinking in my head that it was, if my actuators failed, my amperage would go up because it's trying to do work, but it's not, it's basically more restrictive or more resistance to doing the work. But once I talk to you, then it's like, okay, that makes sense that it's not going to be doing the work because my amperage is not going up anymore.
I love how you said that, and I appreciate you sharing that. You know what I do during the day. I literally field technical support calls from all over the world, and synonymously, no matter what country I'm providing support for, no matter how old or how young the technician is, I see people struggle with voltage drop all the time because they never made sense of it, and it wasn't their fault. They just weren't taught. So here's if you don't mind me sharing what I saw and what my thoughts were when I viewed your video. I thought to myself, as the current began to degrade over time, the work being performed was less and less. So the circuit is failing, whether it's the wiring, whether it's the relay, whether it is a path to ground or a path to voltage supply, or the actuators themselves, there is a failure taking place somewhere. So my thoughts were the failure equates to voltage drop because how voltage and resistance and amperage all relate to one another. That's Ohm's law, and that's where we struggle as technicians. We're taught Ohm's law, like the written word, but we're never taught to really make sense of it. So if voltage begins to degrade, like a voltage supply to an actuator like this, current flow will drop. It'll perform less work because there's less electrical pressure. And the same holds true on the ground side. So we could have an actuator issue. We could have a wiring issue. We could have a relay issue. We can have a ground stud issue, for instance. So speaking of ground studs, going back to the diagram, question for you, Mike, is this is let's see, let me zoom on this a minute. This is G302. Is this G302 common to all four of these actuators?
That it is.
It sure is. So is G302 a potential fault?
Yes.
It absolutely is. So let's do something that many technicians won't do, and it's not their fault. Again, many technicians are groomed to be fast, to keep moving, because time is money in our industry. Whether we are paid flat rate or salary or hourly, time equates to money. So many technicians will start investigating the ground potential at G302, and there's nothing wrong with that as far as accuracy goes. However, efficiency comes into play here. If we want to be efficient, we have to think things through. So rather than spending time at the car, let's just use some logic. So all I did was research G302, and I saw all these components that share G302. And since there was no other issues anywhere else in the vehicle, right, at least nothing viewable here, I leaned against G302 being a problem. So with that, I was considering, again, since you reached out to me, what's the next logical test point? And I thought maybe here, but again, this test point here is for this actuator only. If this test point were a problem, these other actuators would continue to function normal. Do you agree with that?
Yeah.
So rather than testing here, okay, maybe that's not a great idea. I would much rather test here. At least these three share that. I know this one doesn't, but this is an easy to get to test point. So I'd rather test here, but what about this? This is common to them as well. So these are the two test points. All right, so I am demonstrating here using a DVOM simply for, again, demonstrative purposes, but Mike was using his trusty Snap-on Zues 4-trace lab scope, and he was going to perform not only the current test that shows the work being performed, but also this voltage test setup. Now, if you look at the way this is set up, much like your scope is going to be set up, here's what we know. Whatever's displayed here is showing the difference between the two test points. So if we've got full voltage supply and full ground potential, the difference should be about, in this case, 12.5 volts, right near source voltage. And if it's showing this, what this reading means to me is that everything between here is now in question. Here out to voltage, or here out to voltage and here out to ground, depending on which way you push the switches, is good. That's what this test result is telling me. If this is good all the way out to source and this is good all the way out to source, everything in between here is what is in question. So let's go back to your video of you performing this same test, but at this location. Now, I want you guys at home, excuse me, ladies and gentlemen, I want you to consider the data that's going to be presented on the scope. Let's let it play out, and then we'll recap. I'm going to share my sound again, Mike. Please give me a head shake if you hear this. Okay, we're going to play it. We're going to play this one more time. And what we see in green is the voltage drop taking place here. I know there are no numbers on the screen, but I assure you it's a full 12.5 volts. And yellow is the work being performed, the current. So what this tells me here, action-reaction testing. The circuit has everything it needs to work all the way up to our test points. However, the work being performed degrades over time. The availability of voltage stays the same throughout the entire process. So this is really, really good stuff. This one test told us a heck of a lot about what was going on. And there's lock mode. Oops. So the voltage drop tests, our voltage was available initially with the what I will call good current flow, good circuit performance. But then as performance degraded, we did not lose at the voltage drop test. So if we did lose at the voltage drop test, we could say the actuators are not performing well because there is a voltage drop somewhere else in the circuit. Do you agree with that statement?
Yeah.
Okay, the fact that voltage drop remained good across that test point means everything to that test point was good. And the fact that current flow, the work being performed, was degrading over time says everywhere in between our test points is the issue, is where the issue is located. And that's the thought about thinking logically, taking the time to think things out rather than jumping right to the car. So our problem is between the test leads, plain and simple. And that's the takeaway I want you all at home to have. We perform a test. Before you perform a test, I urge you, have some anticipation on what to expect. What are your expectations of that test? Because when you test something on a vehicle, you are asking a question. The test results are the answer the vehicle is giving you. So we definitely want to know what to expect. If I saw 12 volts, that means everything's good up to that test point, 12.5 volts. If I saw less than that, I'd be chasing a problem somewhere else in the circuit. So going back to our wiring diagram, I would love to make our way inboard from here. So our next logical test could be at 314, J314, which is a junction, or J315. This is a junction. But again, I want you guys to think logically. So watch this. Those are located both under the carpet. My arrow here is covering item number 5, but item number 5 is J315. And item number 4 is J314. They were both located within the circle. So to get to this, we'd have to remove the seat and pull the carpet back, or maybe there's an access point where the harness passes through the floor that we can gain access to this junction. But my point is, I'm not saying we shouldn't test here. All I'm saying is maybe we don't want to go there first. I will go to that test point if my other tests point me in that direction. So I don't want to dig myself deep into this vehicle initially, but I will if I have to. So going back to this wiring diagram, Mike, we tested here. The test results from this test prove the problems in between here. We can't test here easily, and we can't test here easily. The next step would be to go inboard from here. Do you agree with that?
Yes.
At this point, it's worth it. I would much rather pull a door panel off than pull a carpet up. Do you agree?
Oh, yeah.
Yeah, especially in this case, because if you pulled the carpet up and did your test, you'd have to put it all back together and still take the door panels apart. But I don't want to ruin the surprise here. So anyhow, now we are going to test at the actuator. Mike committed to pulling a door panel. Which one did you go with, buddy?
Passenger front.
Okay, so Mike went with the right front. And doesn't matter which. At this point, we're committed to one of the 4. So Mike went with the right front. Now, did you pick the right front because it was within this group?
Well, one, yeah, it's within that group, but it's also since we were initially started our testing in reference to this picture, that was right at the fuse box. So
okay,
we
gotcha.
were right there.
Fuse box is right there. Very good. I was going to say it's probably closer to your toolbox. You bum. You didn't feel like walking around.
I was 3 days over from my toolbox.
I'm just kidding. So let's watch this same test. Mike is working his way closer and closer and closer to the actuator. At this point, he's at the actuator because it's the next easiest test to perform. There's nothing wrong with Mike testing under the carpet at all. I don't want to see Mike waste any more time than he has to, because I wouldn't want to waste any more time than I have to. We spend the time thinking at the computer and we carry out the test at the car. I hate thinking while I'm testing. That's not fun. It's very stressful and it's easy to make mistakes. So let's watch this video again. This is at the actuator. So, Mike, I don't want you to say anything. I want to ask a question to people viewing at home, and I know they can't answer me, but I want them to think this through. What do these test results tell you? I'll walk you through the test results. Green represents 12-volt drop across the actuators, the one actuator we're testing now, and they're all performing the same. And yellow represents current flow, and current is degrading over time. Think about that. What does that test result tell you? Mike's going to reveal the answer in a moment, but my hope is that what Mike tells you lines up with what you're thinking. So what's up with the car, Mike? What did it need? And I know you didn't fix the car.
All 4 actuators.
All 4 actuators were bad. Now, Mike had a question. Mike had a question for me. Let me know if you remember this question. I can't remember how you worded it, Mike. It was definitely about how you initially opened up on this Wrench Tales episode, that you said you thought current would increase. And I agree with you under this specific failure. First of all, there are 2 types of door lock actuators. One is a solenoid that you see here, and the other one is more like a DC motor. So a motor with some gears, much like an HVAC control motor, a temperature blend door or mode door actuator or what have you. That's what this design is. And this is the design that's in Mike's car. Mike's suspect vehicle, his Impala. So a solenoid just uses magnetism to stroke the solenoid to make it go fore or aft. And there are no contact points for electricity to travel through. Whereas with a DC motor, one that rotates a gear that drives a mechanism, we've got two brushes, and the brushes carry current to commutator bars. So these brushes wear over time, and the commutator bars can wear over time. The springs that hold the brushes outward towards the commutator bars, and it can cause. This vehicle had well over 200,000 miles on it, and it's almost 20 years old. Right? No, it's
Well,
over 20 years.
that's 2009, so
Oh, '09, yeah.
it's
So
15.
19, 15 years, almost 15 years old. Um, this vehicle um, had some significant wear. And what happened was when you have wear at those brushes, those wear represent resistance or the opposition to current flow, making current flow difficult. But at the same time, as current begins to flow, voltage begins to drop. As voltage drops, it creates heat, and heat creates voltage drop, which hinders current flow. So that's why you see it gets worse over time, because it's a cycle. It gets worse and worse and worse. The noise you heard of the actuator's performance degrading over time was current flow. And the reason why it improved when Mike let it sit for several minutes is because, or several seconds or what have you, is because that heat dissipated. And when the heat dissipated, the voltage drop dissipated. The opposition to current flow dissipated, so it got full current flow potential and full voltage potential, and the current flow would have been high enough to allow that actuator to function as such. So, Mike, if you don't mind me jumping in here before I ask you to summarize what you learned, I just want to point out what fixed this vehicle efficiently. I think, Mike, you and I, besides communicating and waiting for responses, I think we had this thing figured out in like 15, 20 minutes, didn't we? If you add up all the time we spent testing,
Yeah.
something like that. It was really no big deal. But I call these G's and P's, G standing for generalized tests. Generalized tests are tests that give me a ton of information for a small amount of time and or energy invested. I use the results of those tests to drive me closer to the problem. And at the same time I'm getting closer, my testing is going to become more pinpointed. That's what the P stands for. Um, so said another way, if it was very difficult to get these door panels apart, or maybe I needed a special tool to remove them and Mike didn't have the tool, it would make sense for Mike to pull the carpet up then, because I don't want to see Mike have to wait several days to get maybe a special tool or something like that. So you can create as many scenarios as you want, but generalized testing should lead you like stepping stones to the next logical test. One takeaway that I want everybody to walk away from this with is current equals work being performed. If you are not capturing current flow on a lab scope, you are doing yourself a huge disservice. Learn to implement current probe and current probe testing. There are plenty of classes out there to reflect that, and it will change your diagnostics for the good. The tests prove, whether we want to believe it or not, you can't deny the data. And as I always say, Mike, the data doesn't lie. It proves all four actuators are bad. And that's really difficult to walk up to a customer to tell them. It'd be the same as walking into your home and turning on the lights, and the light at the front door doesn't work, and then the light in the living room doesn't work, and then the light in the kitchen and the refrigerator and all the bathrooms and the oven doesn't work. I'd be really surprised if somebody told me I had 12 bulbs that were out. I just wouldn't believe them. But testing proved that all four actuators were bad. And Mike, how much was this repair? Should that customer have decided to do that repair? About $1,000?
I believe it was closer to 2000.
So, Mike, I got to ask you, without putting you on the spot, is there anything that you walked away from that made you a better tech, so to speak, after this experience, after we kind of talked things through, afterwards versus before?
Just another way to understand voltage drop. It's such an important test and it's such a simple test that a person kind of overthinks it.
Yep.
And that's
Very good.
exactly what I was having happen here was I was overthinking it, thinking, okay, my current should go up, not down, as it's trying to do this. But in the end, now you figure out that, oh, well, it's trying, but it can't. So obviously it goes down.
Now, if you had an actuator, let's just talk about one actuator instead of all four of those. If you had an actuator that was bad as this one was with wear, it would perform the same way. Current would dwindle over time as that heat buildup occurred. However, if that actuator was mechanically frozen and the motors were trying to turn, yes, at that time you'd have a similar symptom. You'd hear it not really work, but current would start to increase. And
Yeah.
again, that's the benefit of current flow, because the symptom is what you're hearing, but the current test in this case tells us, is it a frozen actuator or one that doesn't have everything it needs to work? So, Mike, brilliant, man.
Well,
Thank you so much.
And we took it, before we pulled the door panel, we did test at every door jamb with the
Awesome.
same
Good to know.
with the same result as when we were at the actuator and the
So,
initial.
would that be these right here?
I would venture to guess so.
Yeah. Your connectors, that would be at the door jamb where they pass
Yeah.
through the doors.
Yeah, because we just it's a connector in there, so we were able to get in there, back probe, do the same test to verify it on all four. Then we pulled the door panel, did
Now,
it at the actuator, and then I took it one step further. I actually used a jump pack to apply
the
power
actuator.
down to the passenger front actuator with the same results
Good
of
deal.
gradual degradation. I didn't take a scope capture of that, but it was the same
That's okay.
slow dissipating click till
Hey,
now.
and I want to point something out here since you mentioned this. Testing here, for instance, Mike would have put his red lead here, for instance, and his ground lead here, for instance, and tested the actuator. Both these connectors, both these terminals, connector 4, X302, connector 4, X302, connector B4, C4, or I should say row C terminal 4, row B terminal 4, were for the door lock actuator. If Mike had tested there and did not see the 12-volt drop like we're showing here, that proves the circuit is not good up to this point, which would then force him to go backwards, meaning it was justifiable to remove the carpet and access these. But testing here proved you're past the fault, and the fault is internal to your two test leads right here. So, Mike, excellent work, buddy. Excellent work. I appreciate you sharing that with me too, because you're helping a ton of people learn from this. You really are.
That's the name of the game.
Mike, thanks again for joining us on this episode of Wrench Tales. We'll catch all you next time for episode number 5. Take care.